is Alexander Melnichenko.
Yes.
Awesome. From Berea College. Please take it away.
Yeah. Welcome everyone. Thank you for the introduction. Today I'll talk about the introduction of the new measure to study turbulence of a synchrotron emitting screen. Let's start. So first of all, I want to emphasize that the turbulence is very ubiquitous in our universe. It shapes different ranges of the astrophysical formations, I think, like, for example, like galaxy formation or star formation. The presence of a large number of relative electrons in the dense regions of space creates synchrotron emitting screens that their polarization could be analyzed in a model of synchrotron emitting screen and Faraday emitting screen. Such work was presented for the last few decades of research. One of the examples of the analytical analysis is represented, for example, in Lazaryan-Pogosyan 2016 paper, where they presented the analysis for the mixed synchrotron and Faraday emitting screens. Typically, a magnetic field is not presented as a synchrotron emitting screen, and its separated screen of only the Faraday emission screen contains a magnetic field. And in this model, we provide a separated screen. So the synchrotron emitting screen is represented as a galactical gallery, somewhere like in the center of the gallery, where the thermal dense electrons creates the synchrotron emission, and later it transmits through the Faraday emitting screen, where the magnetic field is present and the rotational is applied, and the vector is rotated by some degree. And later, it's very important for observers to analyze the turbulence, since it shapes the formation of objects. So, as I mentioned previously, the possible ways to study were presented in the previous papers. For example, in Hyperchron 2006 paper, there was analysis of the wavelengths that that required us using a large number of arrays of wavelengths. And later in the Lazaryan-Pogosyan 2016 paper, there was provided a derivative measure, which was also had some drawbacks because of the using the derivative, which is not convenient for the observers, as well as a limited case for the Faraday dominated screen. We present a new measure. We call it directional spectrum measure. It's represented as it's grounded on the analysis of source parameters, which is indirectly could be obtained by the observers. Later, the updated polarization maps. We could compute the directional spectrum, which consists of both Q and U maps that could be obtained both from the numerical simulation or from direct observations. Here you can see the representation of the directional spectrum measure for the separated synchrotron and Faraday screen. It's not a synchrotron dominated regime right now, it's transitional regime. As right now you can see there are two asymptotics. The orange line represents here as the Faraday dominated screen, and at small scales the Faraday dominates, and later there is a transitional which corresponds to a specific wavelengths at which the observation occurs, and based on the wavelengths that we see, we have a prediction of where the transition between the intrinsic dominated screen and Faraday dominated screen will occur. If we start with small rotation measure, the intrinsic polarization screen dominates. Later, there is some transition between the two asymptotics, and directional spectrum shows the large correlation with spectroscopy for the Faraday dominated screen at large wavelengths. So here you can see that at small scales there is an intrinsic dominated screen, and later there is a transition to the Faraday dominated screen, which also depends on the wavelengths and the parameters like correlation lengths for Faraday screen and synchrotron dominated analyzing the comparing to the previous known measures. For example, here is a comparison between the primitive measure from the American Astronomical Society paper and our newly introduced measure on the left. We see that our new measure shows a better correlation for the Faraday dimming screen, which is a blue line here, and summarizing the advantages of a new measure, we see that it becomes much easier for observers because we only need one wavelength instead of the whole array of wavelengths. Also, there is no need to compute the derivative measure, and this new measure is complementary to the already introduced measures. So I encourage everyone to look at it. Thank you.
Thank you so much. Thank you so much, Alexander. So we have time for questions. I'll start with a question. So how can you take depth depolarization in Faraday into account in this technique?
Usually, the Faraday depths, like it was firstly described in the 2000 paper, and basically the Faraday depths is the integral of the multiplication of the magnetic field and density over the depths of at which along the line of sight.
And how can you take the depth depolarization into account in this work?
Yeah, so basically, like in our case, we considered the separated synchrotron dominated screen and Faraday dominated screen. The Faraday effect was only affected in the Faraday dominated screen, and the most important advantage of this regime is that we could separate the factor of the polarization from synchrotron dominated screen and the factor from Faraday dominated screen. And because of this, the effect of the Faraday depth is only represented in the Faraday term, and it is just the exponent to the power of 2i, and the Faraday depth term, which is also the exponent of Faraday depth.
We have time for more questions.
Can we do this with less maps? Can we do this with dust polarization maps also?
Yeah, sure. Yeah, so the approach is standard, and it could be applied also. So the most important factor is to occur the Stokes parameters, the polarization maps, and after that you could compute the directional spectrum measure just having the Stokes parameters maps.
And we have time for more questions.
Very nice talk. Can you review again how you learned anything about Faraday effect about Faraday rotation from just one wavelength? That part confused me a little bit because I always think of Faraday rotation as requiring multiple wavelengths to see the effect.
Yeah, sure. Because we focus on the polarization map and we directly compute from the Stokes parameters, the factors that based on our observation, how can we determine where we know the wavelengths, how can we determine whether we are right now in the Faraday dominated screen or in the synchrotron dominated screen. We see as a transitional ratio, we call it, for example, error cross, which is yellow line here, and it represents whether two asymptotics are complement each other. So this transition between two asymptotics, and the regions that corresponds to the spectral index of the Faraday screen, it corresponds to whether we are right now in the Faraday dominated screen, or if it is, for example, in the large scales, it means that we are in synchrotron dominated screen. So we see the transition between two asymptotics. And if you don't see the transition between two asymptotics, and there is only one asymptotic dominated. For example, if wavelength is near zero, so rotation measure is also near zero, there will be intrinsic the term of Faraday emitting screen will be dominated. And usually in observers we see like more shallow Faraday emitting screen rather than intrinsic polarization.
Thank you.
Thank you.
Wonderful. Thank you so much. Thank you for the nice talk. Let's thank Alexander and all